Take your class. So I hope you all can see the screen. This is your syllabus, okay? And there are a few pending things which I need to cover. I want you all to make notes, okay? We have done uh, things like electric field, Maxwell's equation, static fields, potential gradient, okay? And a few more topics are pending, which I am going to now do. The next thing that I'm going to deal with is uh, continuity of current. Okay. So let's look at that topic. Give me a moment. I will share the screen in a while. So you all are able to see the screen, I believe. The topic is continuity of current. Can I have an acknowledgement that you all can see the screen?
Yes, ma'am.
Okay. So we have two types of current density. One is the conduction current density, which is denoted by J bar. And we have the second type of current density called the displacement current density, that is DABA D by DABA T. But the continuity of current is pertaining to the principle of conservation of charges. So charges per se are not the ones which are in the insulator that cause the displacement current, but the ones which are free charges that contribute to the conduction current. So the continuity of current is shown with respect to conduction current density. Now, if we have a region, a closed surface region, then the amount of current that passes through that closed surface is said to be, say, I. So here you can see that I is the total current passing through the closed surface region, which can also be evaluated using the surface integral of J dot ds, as you can see. Okay. Now, what does continuity current actually show you? It actually talks about the conservation of charge in a way. Okay. Now, what was noticed is the outward flow of the positive charge. Okay. When you have an outward flow of positive charge, what will happen if the charges are flowing out, that is the positive charge is flowing out, then we can say that there is an increase of the negative charges inside the closed surface. So they are all related. So if I have a positive charge flowing, that means inside the region, the net negative charges increasing. So you can see here that the rate of flow of current, which is called rate of flow of, charge, which is called current, that is dq by dt, is shown here with a minus sign. Why minus sign? Because it relates to the rate of decrease. So the charge inside the closed surface, which is q, okay, when it is flowing out, it causes the decrease of the charge at a certain rate. That's why you have the minus sign. So the current through the closed surface, I, which we had shown in the earlier expression as closed surface integral of J dot ds, is also balanced with a equation which relates to the rate of decrease of the charge, that is minus dqi by dt. Everybody is okay so far? So we have I, which is shown with two expressions, surface integral J dot ds, which is the current flowing out through the closed surface, and counter to it is the rate of decrease of charge. Okay, that is minus dqi by dt. Going forward, what we have just shown is called the integral form of continuity equation. Okay. Now, what do you see? On the left hand side, I have the closed surface integral. Okay, I hope everybody is understanding this. I have the closed surface integral over here. Okay, the closed surface integral, as you know from divergence theorem, we can also connect it to the point form in this way. So, what happens is the uh, the I, that is the current, surface integral J dot ds, which was equal to minus dqi by dt, can be rewritten in this form. Okay, so you can see the closed surface integral has been brought now to a volume integral using divergence theorem. Now, what happens is in that closed surface, okay, that we were talking of, through which the current was flowing, okay. Now, what happens is there are charges actually which are flowing, okay. There are charges which are flowing at a rate dq by dt, isn't it? Now, if there are charges over here, those charges are present in a volume. That is why we are now going to integrate those charges, okay, dqi, okay, and meaning integrate the volume charge density in order to get the charge inside the volume. So now what happens is in the process at both the left hand side as well as the right hand side, you will now have the volume integral. Now in this case, since we have volume integral, I can get rid of it. And what I am left with is del dot J, okay, and infinitesimally small volume equal to minus daba rho v by daba t into infinitesimal volume. Okay, so now eventually these two will get cancelled, and what I will have in return is a del dot j equal to minus daba rho v by daba t. Now this is your continuity equation. You don't have to remember this derivation, but you have to remember the continuity equation. What does it mean? It means that the current, okay, or charge per second diverging from the small volume per unit volume is equal to the time rate of decrease of charge per unit volume. This is all per unit volume. Okay, so this you have to remember. This derivation I have explained to you, but you have to understand what is the point form of continuity equation. Is there any doubt here? I'll pause here.
No, ma'am.
No, ma'am.
Every, everybody is okay.
Yeah.
Note it down. Please take a while and note down this point form of continuity equation. We will move ahead. Go ahead now. Everybody has noted this. Now coming to I'm using my whiteboard. Okay, now everybody I think can see we will talk of boundary conditions. Okay, you all please make a note of this. Boundary conditions. And in the simplest way, let us take dielectric media. Okay, dielectric media. Okay. Now, does anybody know what is this expression? This is the potential expression, if you see. Okay, this is actually the line integral. Okay, line integral of the static electric field around a closed path. Okay. Now, can anybody tell me if I take the line integral around a closed path? So if this is the closed path, and if I take the line integral of the electric field, so this is the electric field, okay, and if I'm taking the closed line integral, I've gone round and I've taken E dot dl and I come back, what will be E dot dl? It is 0. Okay. In static fields, I had already told you the conservative field, you have closed line integral E dot dl equal to 0. This you please remember. Is that clear? Now, in that case, I'm talking about now boundaries. Okay. What happens to the field at boundaries? Now, suppose this is the boundary. Boundary between what? Boundary between one medium which has permittivity, electric permittivity epsilon 1, and the other one is saying having epsilon 2. Okay. And I am talking of, say, an electric field which is, falling tangent to this boundary. I'm looking at two extreme conditions. One is tangent in this way, and the other one is, I will see, normal. Okay. So let's look at the first case where you have tangential electric field at the boundary of two dielectric media, of course. Okay. Now, so what I will say is that the electric field in medium 1, say, let me call it is ET1. And the electric field that is formed at the other side of that boundary is ET2. Okay. And I'm looking at a very small section of this boundary interface. Very small section. Okay. Such a small section I'm looking at. I'm looking at it piecewise. It is such a small one that this length, I will call it is delta x. Okay. And this length, I will say, is along y. Okay. And it will be delta y. Everybody is okay so far? Okay. Now, I am looking for applying E dot dl. What am I applying? E dot dl. Now E dot dl I am applying in this dotted loop. Is this a closed loop? Yes or no? Are you all with me, students?
Yes.
It
Yes.
is the
Yes,
closed
ma'am.
loop. Yeah. And is it encircling the interface, the boundary? Is it encircling the boundary? A small section of the boundary?
Yes.
Yes. That is why we are looking at this. Okay. And what is happening at the boundary is that the medium is changing. It is going from epsilon 1 to epsilon 2. And I have named the electric field in medium 1 as ET1 and the electric field in medium 2 as ET2. Okay. Now, I am going to apply close integral E dot dl. Okay. So, I'll go round. And when I go round, I will say ET1. Okay. ET1, I'm going to multiply it with the length. What is the length that ET1 is getting applied to?
Delta X.
Very good. Delta X. Okay. Now I'll continue, I'll go around the loop and I am now coming across some component of electric field which I have not declared at the moment. I will simply say something E perpendicular. Okay. Okay. E perpendicular. And what I will say, delta y. Okay, E perpendicular, we will say, is the one which is working in this length across delta y. Now, should I put a plus sign? I'll put a plus sign because we do not know as of now what is the polarity. Okay, and I will multiply it with delta y. Everybody okay with this?
Yes, ma'am.
Now I will go forward. Now I am coming across ET2. Now ET2 is in the opposite direction of ET1. Okay. Okay, so minus because I'm going round and this one is working in this direction. I am moving in the opposite direction of ET1. So I'll have minus ET2 delta X. Next one, the fourth term, I will find is what? Now I'm moving ulta, right, of E perpendicular. If I have taken E perpendicular as positive, now I have E perpendicular which is negative. Okay, so E perpendicular I'll have to put minus and I will multiply by delta y. Okay, now I have completed round this loop and I will say this is equal to 0. Now, what will happen in this process? These two will get cancelled. And what will I see? Whether you like it or not, I will see ET1, okay, delta X minus ET2 delta X equal to 0. Okay. Now, what I am saying, delta X and delta X are same. That means ET1 minus ET2 is equal to 0. Now, what have I proved over here? What have I proved is that if I have a dielectric media and it is having this interface and say there is an electric field which comes across, the tangential components will cancel out at the interface. This is what we have proven here. You can also say that the tangential electric field is continuous at the boundary. Is that clear? So we have dealt with the tangential component. Now, have we finished boundary condition? Do you think we have finished boundary condition? Just by doing tangential component? No, we have to
No.
do the perpendicular component also. Now, again, we talk of the interface. I have epsilon 1 here, epsilon 2 here. Okay. Now, what I will do is very smartly to make my life easier, I'll talk of the perpendicular components, okay, at the interface, but I will not call it E. I will call it dn1 and dn2. Why D? Because then I can use Gauss law, correct? And anyway, D is related to E by this expression. So if I know what happens to D, I will also know what happens to E. Okay. So we will continue with dn1 and dn. So now for the normal component, what I will do is I will create a surface, okay, at the interface. Now, since this interface is planar, okay, I am going to create a box type interface, which is enclosing my boundary between the two dielectrics. Okay, so now this is a closed surface, and the normal component of the flux density, which is crossing, you know, d dot ds. Okay, d dot ds, we know through Gauss law, we know is going to be equal to the charge enclosed, okay, charge enclosed by the surface, okay. Now suppose there is some charge enclosed over here. For instance, there is some charge here at the interface. I will have to show it as surface charge, okay, surface charge. So if at all there is charge, if at all there is charge, then I will have rho s into that area which is enclosed in that Gaussian surface to give me the charge. Okay, if at all there is charge. Now, who will tell me it's the dielectric, right? Dielectrics, do they have free charges? Do they have charge, dielectric?
No.
No, they do not have. Okay, you know that they are known to be insulators. Okay, so they are free of electric charge. Okay, anyway, now this is a very general case that I had spoken. Let us go back to our dielectric media. Okay, so now I'm going to apply Gauss law. That is, I'm going to look at this particular component dn1. Okay, I'll multiply it with the area, okay, the area which it is cutting through. This is that area, okay. In so I will get the flux, okay, total flux cutting that area dn1 into area, okay. And I also know that there is a flux which is entering, okay. So I have dn into area. Area is the same. If I want the net flux which is left behind inside the surface, I will do the subtraction. So we always know by Gauss law that the net flux, so there will be flux lines entering, there will be flux lines leaving, okay? And now, since this is a dielectric media, what will happen over here? Will it be zero or will it be some quantity? Who will tell? Are there free charges at the interface in a dielectric? Free charges are there or what at the interface? Yes or no? So there will be no charges here inside the Gaussian surface. Hence, the net flux will be zero. Hence, dN1 minus dN2 will be zero. Okay? Is that clear? So, the normal flux density at the interface is also continuous. Is there any doubt? Anybody having a doubt? I don't see any response. Are you all listening to me? Are you all understanding?
No, ma'am.
You're not understanding?
No doubt, ma'am.
No doubt, ma'am.
No doubt. Okay. So, what have we understood is dielectric media. Okay. The boundary condition is ET1 minus ET2 is zero. They both are continuous. And dN1 minus dN2 is also continuous. Now, if you have a dielectric metal interface, if you have a metal, there is a dielectric here, okay, and there is metal here. Now, what will be the difference? ET1 and ET2 will be continuous. Okay, remember this. ET1 minus ET2 will be continuous. But dN1 minus dN2 will be equal to rho s. There will be some free charge at the interface. So the normal components will have discontinuity, which is amounting to the free charges. Okay. So this is the boundary condition for the electric field. Next is, have you all studied of Biot and Savart law? Do you all
Yes.
remember Biot-Savart law? Okay, so that is why a lot of things are not mentioned in your syllabus, believing that you guys know the Biot and Savart law. Okay, now there are boundary conditions for magnetic field as well. Okay, now again, suppose I have an interface. Now, whenever it is magnetic field, we will use the magnetic component mu, mu1 and mu2. Now, there are two cases that the the magnetic field will be tangent. Okay, HT1 and HT2. Okay, and again, I am going to take a small loop. Okay. And what am I going to do? I'm going to do a H dot dl. What is H dot dl? This is Ampere's law. Means if I have a current carrying conductor, okay, if I have a current carrying conductor, I have a magnetic field around. Okay, so this is the magnetic field around. Now, if I take this loop, okay, if I take this loop, any loop if I take, and I'm talking of, I'll just show this highlighted. If I take this loop, okay, of the magnetic field, and I multiply H over this loop length, that is, in short, I'm doing a H dot dl, right? What will I get? I will get the current which is present in the center. Okay, I will get the current. If I keep on taking all the magnetic loop rings around over the entire surface, then I'll get the total current. But I'm not doing such a thing. Let us just look at this small ring over here, okay, and do a H dot dl. Again, this is delta x, this is delta y. Okay, now again, what will happen is I'll do a H T1 delta x. Okay, then next, what will happen? I will have a H perpendicular, okay, delta y. Okay, next, that H perpendicular, okay, before that, minus HT2 del x, and then the H perpendicular will be opposing the earlier H perpendicular, delta y equal to what? Can I put equal to 0 here? No. This is going to encircle the current because this is Ampere's law. Earlier, we had a E dot dl equal to 0. That is conservative property. That's a KVL. If you go around the loop, you get the potential in the loop equal to 0. This is Ampere's law. Then you cannot make it equal to 0. You will have to take into account the current which is flowing in the medium, in the interface. Okay. Now what am I left with? These two will get cancelled. I will get a HT1 delta x, HT2 delta x equal to I. Okay. Now HT1 minus HT2 is equal to I upon delta x. That is, this is now some current density, okay, linear current density, so which we can call it, say, K. So the tangential component HT1 minus HT2 for a magnetic field depends upon what current flows, okay, that is K, where K is the linear current density. Now coming to the normal component. Again, we look at the interface. Okay. Now for normal component, as you know, we would love to have Gauss law. So there is U1, U2. We can't use epsilon 1, epsilon 2. That relates to electric field. Mu1, mu2 relates to magnetic field. Okay. So we will take again normal components. So we will take a dabba, a Gaussian box. Okay. To enclose our interface, one small section of our interface. Okay, my interface is called short. Now, what we are going to do, we are going to highlight the normal component D and 2 in the second interface. Pn1 in the first interface. Okay, and this is like some delta Z, right? Okay, yeah, we'll call this delta Z, and this is going to be some area. Okay, this will be some area. Now what we will do, we will use Gauss law. Okay, and we will multiply that Bn1. Okay, that is the flux which is leaving, magnetic flux which is leaving, and what is entering is minus Bn2 into area. Now you know by this Gauss law, magnetic flux lines, they are always continuous. Whatever has entered will always leave. So you will put a 0. Okay. So Bn1 minus Bn2 will be 0. So what you will find is that this is continuous. The normal components of a magnetic field at the interface is continuous. Okay, they will never be able to retain themselves there. They will go out. Okay, so what have you seen? When it is electric field, always the electric field components on the dielectric or the dielectric metal will be always continuous. The normal components, okay, need not be continuous. Okay, only they are continuous in case of dielectric media, and in case of dielectric metal, it will have some kind of discontinuity. In case of magnetic field, the tangential components are discontinuous, they are not continuous, whereas the normal components are always continuous. Okay, so this is about boundary condition. Is that clear? Is that clear? Now, what does it mean? It means that electric field cannot lie tangent to the surface of or interface tangent to the interface between media. Okay, whereas magnetic field can lie tangent because it can take discontinuity. Electric field cannot take discontinuity. Is that clear? समझ में आ रहा है कि नहीं?
Yes,
अरे
ma'am.
कोई है?
Yes, ma'am.
Like, can you summarize what you have understood? Can you summarize? Is Kavya there in the class? Kavya there in the class? Festival,
Yes, ma'am.
what have you followed?
So in we have discussed two boundary conditions, namely for the electric field and for the magnetic field. In the electric field, the dielectric to dielectric media is continuous for both P and D, whereas the normal components in magnetic field at the interface is continuous. Yeah.
So when we see, I'll just give you a clarifying distinction, boundary condition. Okay. If you are talking of E and H. See, don't worry about the derivation. Understand this. Tangential, continuous, always. Be it dielectric, be it dielectric metal. Is that clear?
Yes, ma'am.
Here, tangential component will be continuous. Now, when will it be continuous? Meaning it is zero. Here, when there is no current flowing. Now, when will current not flow? When you have a dielectric. है ना? When
Yes.
you have no free charges, so how will current flow? Then you will have this quantity zero. And this will be continuous. Whereas electric field is always continuous. You take a dielectric, tangential components of the electric field will be always continuous. That is ET1 minus ET2 will be zero. Continuous means ET1 minus ET2 will be zero. But for a magnetic field, tangential component will be continuous. That is HT1 minus HT2 will be zero only when you have a dielectric interface. Okay, is that clear? Here, discontinuous. When will it be discontinuous? When you have a dielectric metal. Is that clear?
And by discontinuous, you mean there will be a value to it.
There will be a value equal to not zero, but some quantity. Okay. I believe you understood that in math, continuous, discontinuous. So you have, this is zero means this is continuous. There is some quantity, so this is discontinuous. Is that clear? Now, for the normal components of the electric field, magnetic field, normal components will be continuous when dielectric media interface. Because there are no free charges. And here, normal components always continuous.
And by normal, you mean perpendicular, right?
Yes, normal to the interface. This will be now electric field will be continuous. But when will it be discontinuous?
Dielectric metal.
Yes. आपको ये याद रखना. You have to remember this. And dielectric metal, this is very important. This will go a long way. Okay. What it only means is that electric field cannot lie tangent to the interface between the media. It requires to stand normal and you have to provide for it. Whereas magnetic field is the one that can lie tangent. That is why power will take different form, either electric form or the magnetic form. Is that clear? We'll go ahead. So we have understood boundary conditions as well. Now coming to pointing theorem, you don't have derivation. You have done pointing vector sometime in your life. Can somebody confirm, please?
Ma'am,
Have
I'm hearing the name for the first time. I'm very sorry.
Okay, very good. So if you have heard it for the first time, then don't worry about the derivation. I will tell you what it means. You know that power, that whenever you studied power, forget about electromagnetics at the moment. What you understood power to be V into I, correct? Now, in case of electromagnetics, we are not using V, but we are using an interpretation of V in the form of E. And I is shown with magnetic field. Does everybody agree with this? E
Okay.
will have volt per meter and H will have ampere per meter. And they curl over each other. Okay. So electric field and magnetic field, this is not the way they exist. Huh? I'm telling you that spatially they are orthogonal to each other. Okay. And they are also in time, they do not exist at the same time. So when electric field is maximum, magnetic field will be minimum. And when magnetic field is maximum, electric field is minimum. They kind of play ping pong with each other. Okay. So this is not the way they visually appear, but what I want to tell you is that they are orthogonal in space to each other. Okay. And also in time, they do not exist at the same time. Now, so, we generally show them like vectors like this. And so we would love to have them curl over each other. So that when you curl over each other, you have a E cross H. Okay. Now, when you have a E cross H, where is the result? The result is normal to both of these, flowing in this direction. And that's the direction of the power. Okay, I showed in the wrong direction. Okay, E cross H. So I should have shown in the other direction, isn't it? Anna? Correct, no? Children. Yes? Are you with me?
Yes, ma'am. Yes, ma'am.
Power. Power should be, got it, na? So if I have a plane, like a paper here, huh? And this electric field and magnetic field are having their dance on this sheet, whatever they are changing, alternating in this plane. My power is not on this plane. It is flowing in this direction out, like an arrow out of this sheet of paper. Is that clear? This is how your power is flowing. So this is actually pointing vector expresses this vector, the power vector. Clear? So moving ahead, we have to actually express this P is equal to E cross H. That derivation is there for you just in case you want to go through it. Okay. Some of you will be wondering how it has come. Okay. So you can go through it and understand. Now, in the end, what you need to concentrate is that this E cross H, okay, which is the power flowing out through a volume. So I have a volume, okay, and this power is flowing out through this volume, okay. And what I have done, I have taken chota E cross H, okay, a del dot E cross H. Everybody knows the meaning of del dot, isn't it? You take tiny volumes, surfaces inside this, closed surfaces inside this volume. And you are trying to integrate it over the entire volume to see the net power coming out from this volume. Okay, so something like this we are doing. So we are doing a volume integral, okay, in order to get the total power coming out from this surface. Does this look similar, identical to something that we have done? Who will tell me what is this? How did I get this? There is a E cross H here. There's a E cross H here. There's a volume integral here with a divergence. There's a surface integral here. This is divergence theorem. Did you all understand this?
Yes.
So, in the derivation which is shared with you on Moodle, this particular left-hand side, no, volume integral, okay, is worked out, okay? It is worked out and you get this. You don't have to derive this for the exam. You have to only understand the significance. So write this thing down. Earlier, we used to have this derivation for the students, mandatory. This is volume. This is also volume integral, dv. There's another term which I am writing below. Surface integral, E cross H ds. Now we will look at the explanation. Can we go ahead?
Yes.
So the term, please write down the term volume E dot J dV represents power dissipated in the volume V. Okay, that's the power dissipated in the volume V. Now, the term minus daba by daba T volume integral H square E square dV represents the stored electric and magnetic energy in the volume. Okay, the term minus E cross H ds represents the rate of flow of energy inward through the surface of the volume. Now, P is equal to E cross H. See, we have the E cross H no here in the expression. Can you see this E cross H here? That's the pointing vector. Okay. So P is equal to E cross H. Okay. Is the pointing vector used to measure the rate of energy flow per unit area. Per unit area at a point. The direction of pointing vector indicates the direction of the instantaneous power flow. Okay. Everybody's clear with this? Clear?
Yes.
Pointing vector, everybody is clear, right? Now, let us do some quick revision. So I have taught you continuity equation. I hope everybody has written that down. I have taught you boundary conditions. I have distinctly shown you the difference between the tangential and the normal components of both electric and magnetic field in case of two different types of media, dielectrics, and dielectric metal. Then we have understood pointing vector theorem. Is everybody okay? Not getting stressed? Everybody is okay? Now, I don't see a feedback. Swara, everything is okay? Neha, okay? Raza, you don't seem to be okay. I saw that
Yes,
emoji.
ma'am.
Neha, okay na? Following?
Yes. Yes.
Okay. What is expected is you are not expected to remember the derivation of continuity equation. Continuity equation is actually your KCL. It's a point form KCL. Okay. Now, what happens in your boundary condition? You please understand the distinction between tangential and normal components. Okay. Don't worry so much about the derivation. Coming to pointing vector also, I told you that pointing vector is nothing but an expression of the power flow. And I showed you there is a derivation which is there on Moodle. Go through it if you are interested. But the main crux that you need to understand is the significance of that the power flow, that is the pointing vector, has so many components. There is power dissipation, there is electric energy storage, magnetic energy storage, and then you have a power flow. Okay, a lot of things are involved when you have power flow in research. Okay, so this, having understood this, let us now look at the revision points. I want you all to pay attention to this. Who will tell me what is the radiation pattern of an antenna? You can Google that out. You can do whatever. What is the radiation pattern of an antenna? Who can tell me that? Quickly. I want some interaction, students.
Graphical
Right.
representation of antenna signal strength, gain, or directive properties.
Very good. You can write this. Okay, also. Please write down. I'm okay with that. Okay, what you said. The radiation pattern. You have already done this during your practicals. Is a graphical representation of the radiation far field properties of an antenna. Very good. Now, what is the next thing you have heard in your practical? What are the things you have heard? Who will tell me? Did you hear of the term isotropic antenna? Can anybody tell me? Anybody has heard isotropic antenna? Have you all heard? Write down. Isotropic antenna. An antenna which radiates equally in all directions. It is a point source and you can draw the pattern of that. It's a sphere. The isotropic antenna is a point source. Finish. This is the isotropic antenna. Everybody okay with this definition?
Yes.
Yes, ma'am.
Yeah. It's like a ball. Now next is opposite to the isotropic antenna is directional antenna. An antenna. What happened to my handwriting? An antenna that radiates in a particular direction and radiates more in a particular direction and less in other direction is called directional antenna. Directional antenna. You can draw a pattern like this. All of you all have seen some radiation pattern or the other. Okay. Next is omnidirectional antenna. Omnidirectional antenna, it is an antenna that essentially has a non-directional pattern in a given plane and directional pattern in orthogonal plane. Example dipole. See, because your dipole in the H plane has a pattern which is a circular pattern. Remember? H plane. And in the E plane, it has like this, directional.
Figure 8.
Yeah. So it is directional in one plane, but it is exhibiting like omnidirectional in the other plane, the orthogonal plane. So that's a omnidirectional antenna. Okay. So in one direction, it is in one plane, it is giving you omni pattern and a directional pattern in the other plane. Correct? Got it? Next, principal patterns. Who will tell me what is principal patterns? The E and H plane are the principal planes of antenna pattern. So what is E plane? It is a plane containing the electric field and the direction of maximum radiation.
Ma'am,
Next is, yeah,
ma'am, Raja is asking for the previous line.
what are you asking?
Raja is asking for the previous line.
Previous slide. Please let me know when you are done.
He is done, ma'am.
Okay. Principal plane patterns. One is the E plane. Next is the H plane.
Ma'am, just for 30 seconds, can you show the previous? Thank you. 1 second. Done, ma'am.
H plane. It is a plane containing magnetic field vector and the direction of maximum radiation. Now here you can show the same example of dipole. You can if you are good at drawing 3D, okay, you can show a dipole here, okay, and you can take a blue pen, black pen, and show this kind of a thing. Okay, I don't know. I'm not able to draw. How will you all draw? It is going to be so tricky to draw. Okay. Here you can show vectors, draw it properly. Show only one, okay? Otherwise it looks very ugly. Show one, okay? And say this is the E plane. This is the dipole. This is the E plane. And then if you have the dipole placed again like this, then this is the H plane. Understanding? H plane pattern. Are you understanding what I'm saying?
Yeah, ma'am.
Then, yeah, draw it properly. Okay. And what is half power beamwidth? Find out what is half power beam.
3 dB.
Definition. Who will tell me? Search. Search. You will get. Tell me what you are reading. Also. Definition of half power beamwidth. Can you repeat slowly?
The power is 3 dB less than the maximum.
The power what? Softly.
3 dB less than maximum.
Is this some definition you are reading from somewhere?
No, ma'am,
Huh?
we just calculate from the graph.
No,
that
I don't want.
um,
I know you understood. I know you understood. But can you give me a way that you will express that? How will you express half power beamwidth is my question. So what you will do is you will show a pattern. If there is a question on half power beamwidth, okay, you will write over there normalized power pattern. Normalized power pattern. Then what you will say, this is 0 dB. You will show this minus 3 dB, and then you will show this line, and you will measure this as HPBW. Okay. The beam width of the major lobe that spreads 3 decibels below the maximum value gives the angular measurement of HPBW, or HPBW can, if you want to define, defined as the angular distance between the 2 points on the antenna pattern main lobe, major lobe, main lobe, that are 3 dB below the maximum gain plot. So HPBW is equal to theta HP left minus theta HP right. So what is first null beam width? Okay, you can show it here. FNBW, first null beam width is defined as the angular distance between 2 points on each side of the major lobe, just adjacent where That is, we are talking about tangent, no? Where the radiation drops to 0. Is that clear? So,
Ma'am, on the graph that we plotted on the polar graph, those were the points that went below minus 16 dB, right?
minus 16 dB.
No, no, no. I'm trying
See,
to visualize on the polar graph.
0, yeah, that 0, no, is a very low value in negative. For us, it was minus 16 dB. For some students, it was minus 18, I believe. Okay, so it's okay. Minus anything below minus 12 was okay for us. And I had given that explanation in the class during the labs one. So now, everybody understood this?
Yes, ma'am.
Yeah. Let me see whether I can download this. Where I-
Ma'am, can you show the next slide?